According to the National Electrical Code, or NEC, you cannot run electrical metallic tubing, or EMT, and install a piece of liquid-tight flexible metal conduit, or LFMC, in the run without pulling a ground wire. The NEC mandates that all metal raceways, which include EMT, must be properly grounded. This requirement extends to any LFMC segments that are integrated within the EMT run. The size of the ground wire to be installed must comply with the specifications outlined in Table 250.122 of the NEC. There is one exception to this rule, which applies when the LFMC is installed within a non-metallic raceway system, such as polyvinyl chloride or PVC or fiberglass conduits. In such instances, the installation of a ground wire is not mandatory. However, if the LFMC is installed within an EMT run, a ground wire is required. The specific size of the ground wire needed will depend on the size of the EMT run. Grounding is a critical safety measure in electrical systems designed to provide a low impedance path for fault currents. This low impedance path facilitates the rapid operation of overcurrent protection devices, such as circuit breakers or fuses, which disconnect the circuit in the event of a ground fault. Effective grounding minimizes the risk of electrical shock and reduces the potential for fire or equipment damage. EMT, due to its metallic construction, serves as an effective equipment grounding conductor when properly installed and connected. This means that in many cases, the EMT itself can serve as the grounding path for electrical equipment connected to it. However, when a section of LFMC is introduced into an EMT run, it creates a point of discontinuity in the grounding path. LFMC, while metallic, is not considered as effective a grounding conductor as continuous EMT. This is because the flexible nature of LFMC and the fittings used to connect it can introduce impedance, which reduces its ability to carry fault current safely. Therefore, the NEC requires that a separate grounding conductor be installed to ensure a continuous and reliable grounding path throughout the entire raceway system, including the LFMC section. The purpose of Table 250.122 in the NEC is to specify the minimum size of the equipment grounding conductor based on the rating of the overcurrent protection device protecting the circuit. This table ensures that the grounding conductor is adequately sized to safely carry the maximum fault current that the circuit might experience. Using the correct size grounding conductor is essential for the proper operation of the overcurrent protection device and for minimizing the risk of electrical hazards. When selecting a grounding conductor for an EMT and LFMC run, it is important to consult Table 250.122 and determine the appropriate size based on the circuit's overcurrent protection. For example, if the circuit is protected by a 20-amp circuit breaker, Table 250.122 might specify a minimum grounding conductor size of 12 American wire gauge or AUG copper. If the circuit is protected by a 60-amp circuit breaker, the table might specify a minimum grounding conductor size of 10 AWG copper. It is also important to ensure that the grounding conductor is properly connected to both the EMT and the LFMC. This can be achieved by using appropriate grounding fittings such as grounding bushings or grounding lock nuts, which are designed to provide a secure and low impedance connection between the grounding conductor and the metal raceway. In the exception case where LFMC is installed in a non-metallic raceway, such as PVC, the grounding requirements are different. Because PVC is a non-conductive material, it cannot serve as a grounding path. Therefore, a separate grounding conductor must be installed within the PVC conduit to provide a grounding path for any electrical equipment connected to the circuit. However, in this case, the LFMC does not create a discontinuity in the grounding path as the entire raceway system is non-metallic. Therefore, the NEC does not require a separate grounding conductor to be installed specifically for the LFMC section. To summarize, when EMT is used in conjunction with the section of LFMC, a ground wire is required to maintain a continuous and reliable grounding path. The size of the ground wire must be determined based on Table 250.122 of the NEC, and the ground wire must be properly connected to both the EMT and the LFMC using appropriate grounding fittings. The only exception to this rule is when the LFMC is installed in a non-metallic raceway system, in which case a separate grounding conductor must be installed within the raceway, but not specifically for the LFMC section. The NEC is a comprehensive set of standards and guidelines for electrical installations. It is developed and maintained by the National Fire Protection Association, or NFPA, and is widely adopted by jurisdictions throughout the United States. The NEC is updated every 3 years to reflect the latest advancements in electrical technology and to address emerging safety concerns. It is essential for electricians, contractors, and other electrical professionals to be familiar with the NEC and to follow its requirement when designing, installing, and maintaining electrical systems. Failure to comply with the NEC can result in serious electrical hazards, including electric shock, fire, and equipment damage. In addition to the general grounding requirements for EMT and LFMC, the NEC also includes specific requirements for grounding different types of electrical equipment. For example, the NEC includes requirements for grounding motors, transformers, and other types of industrial equipment. These requirements are designed to ensure that all electrical equipment is properly grounded, regardless of its type or application. The NEC also includes requirements for bonding, which is the process of connecting together all metal parts of an electrical system to create a low impedance path for fault current. Bonding is an important safety measure that helps to prevent electrical shock and reduce the risk of fire. The NEC specifies the types of bonding conductors that must be used, as well as the methods for connecting them. Grounding and bonding are complex topics, and it is important to consult the NEC and other relevant resources to ensure that electrical systems are properly grounded and bonded. It is also important to seek the advice of a qualified electrical professional if there are any questions or concerns about grounding or bonding requirements. Proper grounding and bonding are essential for the safe and reliable operation of electrical systems. By following the requirements of the NEC and other relevant standards, it is possible to minimize the risk of electrical hazards and protect people and property from harm. Now, let us delve deeper into the practical aspects of grounding EMT and LFMC systems, expanding on the core principles already discussed. The selection of appropriate grounding fittings is paramount. Grounding bushings, typically made of metal with a set screw, are designed to securely connect the grounding conductor to the EMT. The set screw bites into the EMT, establishing a reliable electrical connection. Grounding locknuts, another common fitting, are used to bond the EMT to a metal enclosure. These locknuts have a sharp edge that penetrates the enclosure's paint or coating, ensuring a good electrical bond. When installing these fittings, it is essential to clean the surfaces of the EMT and the enclosure to remove any dirt, rust, or other contaminants that could impede the electrical connection. Applying an antioxidant compound to the surfaces before connecting them can further enhance the conductivity and prevent corrosion over time. The size of the grounding conductor, as determined by Table 250.122, is crucial. Using a conductor that is too small can compromise the grounding system's ability to safely carry fault current, while using a conductor that is too large is unnecessary and can add to the cost of the installation. The grounding conductor should be installed in a manner that protects it from physical damage. It should be routed along the EMT and LFMC, and it should be securely fastened to prevent it from becoming loose or disconnected. The grounding conductor should also be protected from corrosion. If the conductor is exposed to moisture or other corrosive elements, it should be coated with a corrosion-resistant compound. In situations where the LFMC is exposed to excessive movement or vibration, it may be necessary to use a flexible grounding braid in addition to the grounding conductor. The grounding braid provides an additional grounding path that is more resistant to the effects of movement and vibration. It is important to note that the grounding requirements for EMT and LFMC can vary depending on the specific application. For example, in hazardous locations such as those where flammable gases or vapors are present, more stringent grounding requirements may apply. In these situations, it is essential to consult the NEC and other relevant standards to ensure that the grounding system is adequate for the specific hazard. Regularly inspecting and testing the grounding system is vital to ensure that it is functioning properly. Grounding connections should be visually inspected for signs of corrosion or damage. The resistance of the grounding system should be measured using a ground resistance meter to verify that it is within acceptable limits. If any problems are detected, they should be corrected immediately. In addition to the requirements of the NEC, there may be local codes or regulations that apply to grounding systems. It is important to check with the local authorities to determine if there are any additional requirements that must be met. Grounding systems should be designed and installed by qualified electrical professionals who are familiar with the NEC and other relevant standards. These professionals have the knowledge and experience necessary to ensure that the grounding system is safe and effective. Continuing education is essential for electrical professionals to stay up to date on the latest changes to the NEC and other relevant standards. This education helps them to maintain their skills and knowledge and to provide the best possible service to their clients. Grounding is not just about meeting code requirements, it is about protecting people and property from the hazards of electricity. A properly designed and installed grounding system can save lives and prevent costly damage. It is a fundamental aspect of electrical safety, and it should never be taken lightly. Remember that electrical work can be dangerous, and it should only be performed by qualified individuals who have the necessary training and experience. If you are not comfortable working with electricity, it is best to call a qualified electrical professional. Understanding the specific requirements of NEC Table 250.122 is vital for correctly sizing the equipment grounding conductor. The table is organized based on the size of the overcurrent protection device, such as a circuit breaker or fuse, that protects the circuit. The table provides the minimum size of the grounding conductor based on the ampere rating of the overcurrent device. It is crucial to use the correct ampere rating of the overcurrent device when consulting the table. If the overcurrent device is underrated, the grounding conductor may be too small to safely carry fault current. If the overcurrent device is overrated, the grounding conductor may be unnecessarily large. The table typically specifies the minimum grounding conductor size in American wire gauge, or AUG, for copper conductors. Aluminum conductors are also permitted, and the table provides the equivalent AWG size for aluminum. It is important to use the correct type of conductor when installing the grounding system. Copper conductors are generally preferred due to their high conductivity and corrosion resistance. However, aluminum conductors can be used in certain applications, provided that they are properly installed and protected from corrosion. The table also includes footnotes that provide additional information and guidance on selecting the appropriate grounding conductor size. These footnotes should be carefully reviewed to ensure that the grounding system complies with all applicable requirements. In some cases, the table may specify a minimum grounding conductor size that is larger than the size of the circuit conductors. This is because the grounding conductor must be able to safely carry the maximum fault current that the circuit might experience, even if the fault current is higher than the normal operating current of the circuit. The NEC also includes requirements for the installation of ground clamps, which are used to connect the grounding conductor to a grounding electrode, such as a ground rod or a metal water pipe. Ground clamps must be listed for the purpose and must be installed in accordance with the manufacturer's instructions. The NEC also includes requirements for the location of grounding electrodes. Grounding electrodes must be located as close as practicable to the electrical service entrance. They must also be located where they are not likely to be damaged by physical contact or corrosion. The NEC also includes requirements for the identification of grounding conductors. Grounding conductors must be identified by a continuous green color or by a continuous green color with one or more yellow stripes. This allows electricians and other electrical professionals to easily identify grounding conductors and to ensure that they are properly connected. Grounding is an essential aspect of electrical safety, and it is important to follow the requirements of the NEC and other relevant standards to ensure that electrical systems are properly grounded. Now let's address some common misconceptions regarding grounding EMT and LFMC. One misconception is that if the LFMC section is short, a separate grounding conductor is not necessary. While there is no specific length exemption in the NEC for LFMC in EMT rounds, the code mandates a grounding conductor regardless of the LFMC length. Another misconception is that using watertight fittings on LFMC automatically ensures proper grounding. While watertight fittings are important for preventing moisture from entering the raceway, they do not guarantee a reliable grounding path. A separate grounding conductor is still required. Another misconception is that the EMT itself provides adequate grounding, even with the LFMC section. While EMT does provide a good grounding path when continuous, the introduction of LFMC creates a discontinuity that necessitates a separate grounding conductor. Another misconception is that the size of the grounding conductor only needs to match the size of the circuit conductors. As previously stated, the grounding conductor size is determined by the overcurrent protection device rating as per NEC table 250.122 and may be larger than the circuit conductors. Now, let's discuss some advanced grounding techniques for complex EMT and LFMC systems. In situations where multiple EMT runs converge at a junction box, it is important to ensure that all of the EMT runs are properly bonded together. This can be achieved by using grounding bushings and bonding jumpers to connect the EMT runs to the junction box. In high-noise environments, such as those where sensitive electronic equipment is used, it may be necessary to use shielded EMT and LFMC to reduce electromagnetic interference, or ME. Shielded EMT and LFMC have a metallic shield that surrounds the conductors and helps to block EMI. In corrosive environments, such as those where chemicals or saltwater are present, it is important to use corrosion-resistant EMT and LFMC. Corrosion-resistant EMT and LFMC are made from materials that are resistant to corrosion, such as stainless steel or PVC-coated steel. In situations where the grounding system is subjected to high fault currents, it may be necessary to use a ground fault protection system. A ground fault protection system is designed to detect ground faults and to quickly disconnect the circuit to prevent damage to equipment and to protect people from electrical shock. Grounding and bonding are essential aspects of electrical safety, and it is important to follow the requirements of the NEC and other relevant standards to ensure that electrical systems are properly grounded and bonded. When dealing with specialized equipment or installations, always consult with a qualified electrical engineer or inspector to ensure compliance with all applicable codes and regulations. The information provided here is for general guidance only and should not be considered a substitute for professional electrical advice. Now consider the specific scenario again. The LFMC is used to transition between elevations. This means there is a physical break in the EMT run. Even if the distance is short, the NEC requires a grounding conductor to maintain the integrity of the grounding path. Without it, a fault could energize the conduit, creating a shock hazard. Consider the consequences of a fault. Without a proper grounding conductor, the fault current may not be sufficient to trip the overcurrent device, such as a circuit breaker. This could result in a sustained fault, leading to overheating, fire, and potential injury. The grounding conductor provides a low impedance path for the fault current, ensuring that the overcurrent device trips quickly and safely. In addition to safety, proper grounding also helps to reduce electrical noise and interference. This is especially important for sensitive electronic equipment, such as computers and medical devices. A well-grounded system can minimize the effects of EMI, ensuring that the equipment operates reliably and accurately. Now, let's explore some common grounding mistakes to avoid when working with EMT and LFMC. One common mistake is failing to properly tighten grounding fittings. Loose grounding fittings can create a high resistance connection, which can compromise the grounding system's ability to carry fault current. Another common mistake is using the wrong type of grounding fitting. Grounding fittings must be listed for the specific application and must be compatible with the type of conduit being used. Another common mistake is damaging the grounding conductor during installation. The grounding conductor must be protected from physical damage to ensure that it remains effective. Another common mistake is neglecting to inspect and test the grounding system after installation. A thorough inspection and testing are essential to verify that the grounding system is functioning properly. Avoiding these common mistakes can help to ensure that the grounding system is safe and effective. Now let's recap the key points. Firstly, EMT requires grounding. Secondly, LFMC in an EMT run necessitates a grounding conductor. Thirdly, NEC Table 250.122 dictates the grounding conductor size. Fourthly, proper grounding fittings are essential for secure connections. Fifthly, regular inspection and testing are crucial for maintaining grounding integrity. Finally, consulting with qualified professionals ensures compliance and safety.